Okay, so we're going to talk about some trends that exist in aqua acid strength, and then we'll talk about some other trends in other types of acids as well. So remember, aqua acids are acids that have coordinated water, and the acidic proton is coming from that coordinated water. Smaller, higher charged ions have greater acidity. Um, So if you look at, for example, looking at hexaaqua sodium ion cation versus hexaaqua lithium cation, lithium is smaller than sodium because it's right, a period above sodium. Lithium is about 1 pKa unit stronger. Um, you can also look at charge, so you can look at hexaaqua iron 2 versus hexaaqua iron 3 cations, and that makes a bigger difference in this case. About the one with the higher charge, the 3 plus, is 7 pKa units more acidic, right? So that would translate to what, 10 million times more acidic, 10 to the power 7. Why would something that has a smaller, higher charge give rise to greater acidity? Well, the idea is that what is an acid? An acid is something that gives up a proton. And so if you are a higher positive charge, you want to shed positive charge away from you, right? So that explains, why a more greater positive charge would definitely be more acidic. Why would smaller size be more acidic? Well, you have more charge density. So the lithium ion here has, only 1 plus charge, just like the sodium, but it's on a smaller area, so there's more charge density there. So it's per area more favorable to get rid of that proton and make this a neutral species, okay? Versus sodium, which that plus charge can be more diffuse over one area, and so it doesn't make as big of a difference. So what people have tried to do is develop models that can predict the acidity of these aqua ions, and it's very simply done. We just said it has to do with charge density. And so how do you get charge density? Well, you can come up with this electrostatic parameter z squared, that's the nuclear charge, over r, the size, the radius of the ion. And you can come up with an empirical kind of best fit. You can plot all the data, come up with a line, and come up with this equation of what the pKa should be based upon this electrostatic parameter, where, if you're higher charged, this is going to be a bigger value. So you're going to have a lower pKa. There's a minus here, right? Lower pKa is more acidic. Or if you have a bigger, or let's do it the other way. Let's do a smaller size, right? This will be a smaller number for R, smaller number than denominator. That's going to make this bigger, more negative, and again, more negative pKa means more acidic. So either from a charge standpoint or size standpoint, this equation matches. You can see it's actually fairly good, but there's some deviations, and this is because there's some covalent nature to bonding a lot of times, especially with some of these that are big outliers. So it's not an ionic model for how bonding works in these models isn't a good descriptor. And so there's some electron sharing that can happen that can cause these water to be bounded more tightly than you might expect from just this ionic or electrostatic model. Trends in hydroxo acid strength. Here, one very clear trend is that if you have more adjacent oxygens, you have greater acidity. So it's going to be for oxo acids and hydroxo acids. We're kind of doing these together. Linus Pauling came up with a rule, just kind of empirical rule that said the pK is going to be about equal to 8 minus 5p. This is pretty interesting in that there's nothing said here about chemical identity, about what elements are on the acid. It's just saying that this, his claim is that this is broadly true, and it is actually. It turns out the most, generally speaking, the most important parameter are these adjacent oxo residues. So P is the number of the non-adjacent, non-acidic adjacent oxygens. So if you have more oxygens by it, oxygen's electronegative. And if you have more oxygens by it, this pK value is going to go down because 8 minus 5p. And so down pK means more acidic. So more non-acidic adjacent oxygens makes that acidic proton more acidic. Why would an electronegative element make something more acidic? Well, it's because, again, you're trying to shed a proton, you're trying to shed a positive charge when you're something very acidic. And if you can be electronegative, what is that doing? That's pulling electron density away from that proton, right? And so that makes it even easier to get rid of that proton. Because if electron density is away from the proton, then the plus can go away. But if you have electron density close to the proton, you have a minus and a plus very close to one another, that's going to be less favorable. So electronegative atoms that are adjacent tend to increase the acidity. We'll see more examples of that on the next slide. But here's just looking at the non-acidic adjacent oxygens with different p-values. So p equals 2 means these are various, or let's do p equals 3. P equals 3, these are very acidic species. The only one shown here is perchloric acid. This means it has 3 non-acidic adjacent oxo groups. So there they are, 1, 2, 3. And you can see this is the acidic proton that's in the OH group. So that's a pK of -10, very strong acid. P equals 2, you can see less acidic, but still very acidic. These would all be strong acids. What are these? This is sulfuric acid, nitric acid here, and this would be chloric acid. And then you have cases where there's P equals to 1, and this is where you only have one adjacent oxo group. So there's a bunch here shown. Some of these have multiple pKa's, right, because they have multiple acidic protons. But really what you would want to look at is the first acidic proton, so phosphoric, to do this comparison with Pauling's rule, right? Of course, pK2 is always less acidic than pK1. Because why would that be? pK2, if you have a diprotic acid, let's say this one, carbonic acid, well, that's not given, value's not given there. Let's do phosphoric acid, it's triprotic acid. pK1 is less than pK2, then less than pK3. That will always be true for any acid because when you deprotonate the first one, you're a -1 charge. When you deprotonate the second one, you're a -2 charge. And so to stabilize a -2 charge, nature doesn't like building up a lot of charge in one area. So making a -2 charge versus a -1 charge is much less favorable. Therefore, it's not as strong of an acid. Same thing for making a -3 charge versus a -2 charge. So you can see that's why these pK values go up in succession for a triprotic acid like phosphoric acid. But the point here was that this is in the column of P equals 1. You have one non-acidic oxo group here, one non-acidic oxo group here, carbonic acid, one non-acidic here for chlorous acid. This is phosphorus acid, okay? Yeah, that's correct. And still one non-acidic proton here. So you can see the values here are all kind of similar. They're ranging from what 1.6 to 3.6 for the pK1s. And then these are the hydroxo acids. So they don't have the definition of hydroxo acid is that P equals 0. Doesn't have any of these adjacent oxo groups. So hypochlorous acid and others here, boric acid, have much higher pKs. What about substituent effects? So this gets into usually talking about electronegative atoms or electropositive atoms. So like I said on the previous slide, electronegative atoms stabilize that anion. So they really always usually increase the acidity compared to non-substituted acids. So the acetic acid series is a great example. So look at acetic acid. It's a weak acid with this acidic proton here on the carboxylate group. It has 4.76 as its pK. But then if you go to iodoacetic acid, you can see it gets a little bit more acidic, about 20 or whatever, I don't know the math on that, but more than 10 times more acidic. Iodine is slightly more electronegative than hydrogen, right? So there's a little bit there. And then you go bromoacidic acid, chloroacidic acid, and fluoroacidic acid. And the trend there is that as you're going up on the periodic table, you're getting more and more electronegatives. So fluorine is the most electronegatives and element that there is, right? And so as a result, you can see the fluoroacetic acid is more acidic than the chloroacetic acid, which is more acidic than the um, bromoacetic acid, than the iodoacetic acid. All right, and you can also look at trends in this way where you're just adding more electronegative atoms. So look at difluoroacetic acid compared to monofluoroacetic acid compared to trifluoroacetic acid. And I mean, by the time you're at difluoro and trifluoroacetic acid, these are strong acids. Definitely trifluoroacetic acid. Now everybody would agree this is a strong acid. pK very close to 0. So that's pretty impressive. You basically took a very weak acid, something that I'm comfortable drinking, to something I would never want to drink, okay, in trifluoroacetic acid. You can go the other way. So if you put something electropositive, it can be hard to find electropositive or electron donating groups that don't also contribute some resonance structure, which can affect the acidity in some different way. But one example I was able to find is this is called pivalic acid. So basically, compared to acetic acid, this is these H's got replaced with methyl groups. So carbon, that's an electropositive element. So you put a bunch of those on, and you can see it's not a big change here, but it is getting less acidic. So that effect makes sense.